In this video, I'm going to be going over some information that's generally applicable to the interpretation of photon dose distributions. It will help with understanding how changing things like field size, beam energy, and source-to-surface distance can affect the shape of dose distributions. Remember that for each photon interaction that may cause one ionization, a secondary electron is produced that will cause on average several 100,000 more. So it's secondary electrons that deposit the vast majority of the dose in a photon beam, not the photons directly. Dose distributions in LINAC photon beams are also generated by a number of different sources. The first is the primary beam, so photons that make it from the target to the patient without hitting anything in between. Many photons are scattered as they pass through a LINAC treatment head, most often in the flattening filter and beam collimators. We call these head-scattered photons. Because they've undergone interactions before they strike a patient, they'll have a slightly different energy spectrum from the primary beam. They also travel very different paths, so they don't diverge from the source in the target. The beam is also scattered as it passes through a patient or a phantom that we may irradiate as a patient's substitute. We call this phantom scatter. There are also secondary electrons generated within the LINAC treatment head, mostly within the flattening filter. These electrons are referred to as electron contamination. They deposit their dose very close to the surface and are therefore responsible for the majority of photon beam surface dose. When attempting to understand why dose distributions look the way they do, remember that electrons are responsible for delivering the dose, and that they leave essentially a continuous trail of dose behind them as they move. Therefore, the amount of dose to a given area or a target is proportional to the number of electrons that are passing through it. It's also important to note that by extension, the dose to a point doesn't come from the photons that hit it. It comes from electrons produced by the surrounding irradiated material that pass through it. This is because at any given irradiated point in a medium, photons will be undergoing interactions like the photoelectric interaction, Compton scattering, and pair production. As a result, secondary electrons will be emitted from this point, as will scattered photons. The distribution of dose deposited around these points by these electrons and photons has a particular shape. This depends on the characteristics of the beam emitted from the treatment head, so the energy of the photons, and the angle at which they tend to be traveling. It doesn't depend on depth in the patient. The amount of dose deposited around each point does depend on the depth, because at greater depths you tend to have fewer photons. But the distribution or shape of dose deposition doesn't change. If we have a certain number of photons that deposit 1 gray of electron dose and 1 gray of scattered photon dose around a point, then decreasing the number of photons by half, for example by moving to a greater depth, won't change the shape of this distribution, but it will result in half a gray of electron dose and half a gray of scattered photon dose surrounding this point. It can be helpful to look at dose distributions as a sum of lots of little dose distributions around each point within the beam. There are a few different ways that we like to show dose distributions. The simplest correspond to how physicists actually perform measurements. When taking detailed measurements, we use something called a scanning water phantom. It's basically a tank filled with water. It also has a drive mechanism that allows us to move a radiation measuring device through the beam while it's on, inside the water that we use to simulate patient tissue. When taking measurements, it can only move the detector up and down and from side to side at different depths. So we normally measure dose distributions in these directions as well. The tank itself is normally placed at a fixed distance from the source, which we call the source-to-surface distance, or SSD. If we take measurements whilst moving our detector up or down while the beam is on, we get something called a percentage depth dose curve, which tells us how the dose deposited by the beam varies with depth. If we move the detector from side to side while the beam is on, we call this a beam profile. We can measure these at any depth we like. Treatment planning systems are able to give us a more sophisticated representation of dose distributions in 2 dimensions on a computer screen. This can take the form of an isodose plot, which is a set of lines that connect points with equal doses. It's useful for determining if we're covering a target volume with enough dose. If the isodose line that represents the prescribed dose wraps all the way around the target, it means that the entire target is getting at least the prescribed dose. We can also use a dose color wash, with red generally being higher dose and green and blue being lower dose. During the next few tutorials, I'm going to be discussing the relevant features of some of these, and how they can be affected by variables like beam size and energy.